The example I'm going to use for radical chain mechanism is the addition of HBr in the presence of peroxides to give an anti-Markovnikov HBr. Like all radical chain processes, this reaction occurs through initiation, one or two steps that occur only a few times, propagation, a process that occurs over and over again to produce the majority of the product, and termination. The initiation process for this reaction involves two steps. First, we have homolytic cleavage of the OO bond in the peroxide. This is a very weak bond and will easily divide, and because oxygen and oxygen are of the same electronegativity, when they divide with one electron each to give two radicals to begin with. Notice the curved arrows that we use to define one electron. In smart work, these curved arrows are created by making a double-headed arrow and then clicking on the arrowhead to make a single-headed arrow. This process needs to only happen a few times to make a few active radicals, as we will see as we can proceed with the reaction. Any one of those RO radicals can contribute an electron, along with the HBr contributing an electron, along with the HBr contributing an electron, to make a new bond. This also leaves one electron left behind on a bromine for a new radical species and an alcohol. We are now ready to begin the propagation process. The propagation reaction consists of two steps. It starts with our active bromine radical made at the second step of our initiation, reacting with alkene. The alkene reacts by providing one electron to combine with one electron from the bromine and make a new bond. Meanwhile, the second electron from the pi bond gets placed on the carbon. This is where the selectivity of the reaction takes place, making a secondary radical instead of a primary radical. Recall from the previous slide that secondary radicals are more stable than primary radicals, just like the electron-deficient cations, secondary is more stable than primary. In the second radical step, the secondary carbon radical reacts with a hydrogen from the HBr, and the HBr bond breaks, providing one electron to make a new bond between hydrogen and carbon, and a second electron back on a bromine radical. This allows us to make our second bond of our anti-Markovnikov alkene, and it makes a new bromine radical. We can then start the whole process all over again with this bromine radical reacting with a new molecule of propene to create a new bromopropyl radical, which reacts with another equivalent of HBr to make another molecule of the product, plus another bromine radical, and it goes around and around and around and around and around. Because there is usually a low concentration of radicals at a time, this cycle can continue many times, 10, 100, or even 1,000 before something else happens. And in the process, it creates your major product, 1-bromopropane. Now, even though the radicals are present in very low amounts, occasionally one radical will run into another. If the two radicals that happen to run into each other are both bromine atoms, then we will make a molecule of dibromide. If the two radicals that happen to run into each other are a isopropyl bromo radical and a bromine radical, we would make dibromopropane. And if two isopropyl bromopropane groups run into each other, we would create a 6-carbon dibromide. Again, these termination steps are rare because there is a low concentration of radicals at any time. Propagation steps repeated over and over again are responsible for the major formation of the product. Initiation steps need only happen a few times to start the process. And the anti-Markovnikov regioselectivity is set in this first propagation step, in which the bromine chooses to react with the terminal carbon to make a more stable secondary radical rather than a primary radical. Now, in addition to talking about the electron movement and bond changes, we can also talk about the energetics of these reactions. So, for example, The first initiation step involves breaking an OO bond. When you break a bond, it always costs energy. In the case of an OO bond, it's about 200 kilojoules per mole. And that only happens because you have just the right amount of heat or light in reaction to break that bond. And it only needs to happen a few times. The second initiation reaction, in which an RO dot coordinates with a hydrogen, replacing it to give a bromide radical, is a net exothermic process. Breaking the HBr bond costs 368. Making the OH bond gives off 400 kilojoules per mole for a net exothermic process. During the propagation step, each time we break a bond, we also make a bond. So for in the top reaction, we break a CC pi bond, costs us 263 kilojoules per mole, but we make a CBr primary bond, which gives off 298 kilojoules per mole for a net and exothermic reaction of 35 kilojoules per mole. In the second propagation session, we break an HBr bond, which costs us 366 kilojoules per mole, but we make a secondary CH bond, which provides 417 kilojoules per mole for a net exothermic reaction of 48. And finally, our termination steps are highly exothermic. They involve making a bond without breaking any bonds. And so they are exothermic by the strength of each of the bonds. In the BR-BR case, it's 192 kilojoules per mole. In the secondary C-BR case, it's 290 kilojoules per mole. And in the secondary carbon case, it's about 360 kilojoules per mole. Anytime two radicals encounter each other, they almost always react very exothermic. Let's also look at one example of an electron-proton process, one that is similar to the way reductions are done in, for example, the electron transfer process in biological systems. These reactions require alkali metal that is relatively easy to oxidize. It wants to give up an electron, and a pi acceptor. In the case of the alkyne, the pi acceptor is a LUMO of one of the CC pi bonds. When the lithium gives up one electron, it becomes lithium plus, and it puts that electron into the pi star of the C triple bond C. The C triple bond C bond is no longer localized between the two carbon atoms. The extra electron sits onto one of those carbon atoms to make an anionic center, which is now sp2, and a radical remains on the other. Where there used to be 2 electrons, there are now 1, 2, 3. This is a very strong base, being a negative charge on carbon, and so it's going to react with whatever proton donors you happen to have. When ammonia is your solvent, your proton donor, notice the double-headed arrow, the carbanion grabs onto the H, leaves behind an NH2-, and we've now neutralized the species by getting a radical intermediate. That radical intermediate is electron deficient at the radical center where there's not a octet, and so another molecule of alkali metal will give up a second electron to make a new carbanion. And your new carbanion, once again, is a good base and will grab a proton, notice the double-headed arrow, leaving behind an NH2 group. So that at the end, you've actually created 2 equivalents of lithium plus NH2- as counterproducts and transalkene. The stereochemistry is actually determined in these last 2 steps. That is, the anion is sp2 hybridized, and it will tend to make the larger alkyl group move, for steric reasons, as far from the other alkyl group as possible, so that when you get the protonation in the last step, you end up with your trans product. So reactions 1, 2, 3, and 4 all involve initiation, propagation, and termination, where propagation makes the major amount of the product, and if you add up the propagation steps, you get the net balance reaction shown. The first and second ones are just replacement of a CH on an alkane-like position, either directly at an alkane or at an allylic or benzylic position with a halide. The third is an addition reaction with an anti-Markovnikov regioselectivity, different from anything we've seen so far. And the fourth is a way to look at polymerization, again through a radical process. The last 2 reactions we looked at involved electron-proton transfer, in which the alkali metal would give one electron to a LUMO, creating a radical anion, which is protonated, which would get another electron, making another anion, which is protonated. In the case of the alkyne to alkene, the proton source with the solvent, liquid ammonia. And in the case of benzene or substituted benzene, the proton source is an alcohol.